Hi guys. A couple of months ago, we did a video on quantum supremacy, but I think it was one of our sort of worst videos in terms of how we actually shot it. So we're going to actually do a new one where we talk a little bit more about what is quantum supremacy and just give you sort of the fundamentals of it. So today we've got Junheng, who he's actually, full-time working on quantum supremacy, just submitted a paper on the archive. If you're interested, go and check it out. So you're very well placed to talk about this. So take it away.
Hi, everyone. In this video, we are going to talk about quantum supremacy. Ever since this word is introduced, that it has caused many controversies, and many of them come from quantum and a few from supremacy. Quantum supremacy arises from the concept of quantum computers, which is because of the Shor's algorithm that many people expected to break the encryption, because the major encryption method now we're having is based on factoring. So they are expecting the quantum computers to break encryption. And the other common method is for quantum simulation, because using a quantum system to simulate a quantum system sounds a fair idea. And we have a lot of quantum systems that are waiting to be simulated because they are scales too exponentially and it cannot be really efficiently simulated with the classical computers. What about mining Bitcoin? Well, actually, no, it's wrong. We cannot use a quantum computer to mine Bitcoins. Well, we actually have a previous videos about it presented by Merrick. So if you still don't know about that, you can check that episode. So quantum computers that you expected, all the functions, the expectation we listed here cannot be really realized by quantum supremacy machines at present, because all this requires error correction. And error correction requires a large number of qubits in the quantum computers, which is not available right now. So quantum supremacy is not outstrip the classical computers wherever you like, but actually in one task. Well, it's not really an official definition. It's just looking at the present quantum supremacy demonstrations that you can give this kind of conclusion. And why? I want to quote from Scott Arolsen. So he was saying that you don't need to prove a dolphin's intelligence by teaching to solve arithmetic problems, because quantum systems right now, like quantum computers, cannot do error correction, and enables it to do more complicated tasks and factoring text, for example. But still, in some of the ways and in some specified tasks, you can still show that the quantum system is better than in classical computers in terms of computational power.
So what? Hold on. The dolphins, it's not matching like their abilities. Is that the point?
No, it's like that dolphins intelligent, but you cannot show that by ask them to arithmetic problems. So they are enabled to solve the arithmetic problems. That mean they are not intelligent. So the quantum system right now cannot factor integers because it's not capable. But it doesn't mean it's
So it's just like it's too specific of a problem to show.
Yes, to show that
it's not like a universal problem that shows intelligence. Yeah.
Yes, exactly. I think that's the idea behind the real idea of quantum supremacy, in terms of quantum supremacy is doing everything you can, that kind of supremacy. Okay, so the quantum supremacy is like you have to realize on quantum system, that's of course. But in some specified tasks, that it can outstrip the fastest simulation from classical computers. And it's also using the fastest algorithms, and also these algorithms can be run on the fastest supercomputers. So they are really competing with the best the class computers can offer, to get this kind of a goal. The first quantum supremacy demonstration from Google, that's a group led by John Matisse, and in 2019. And in this experiment, managed to sample a quantum circuit 1,000,000 times in 200 seconds, while the state-of-art classical supercomputer would take approximately 10,000 years to do that. So, and what are actually in this kind of superconducting processor made of, and what's actually behind that? So it's their chip. You can see that this is what actually inside the chip, and you can see that there are the nodes, like nodes. The nodes are the qubits, and the connection of the nodes are gates, which connect the qubit.
So the crosses are the qubits.
Yes, the crosses
are the qubits. Okay.
Yes.
Yep.
The idea is that so there's a 2D setup that so you can have the qubits where every qubit linked to 4 other qubits by 4 gates. And if you look at the bottom, and you can see closely at 1 qubit and how it works. For example, so here that they give you 5 qubits as a example, that you can see that how this 5 qubits evolve under the different sequence of the gates. For example, that the A gates operate first, and then the B gates, and then the C, and then D, and this will have a circle. And then after all the sequence of this 2 qubit gates, and you put a measurement to every qubit, and then you will have a bit stream. Right, so each one is indicating that 1, 0, I think, and so in this kind of sequence, you were able to produce one example of a bit stream, right? And the idea of this processor is to produce that millions of this kind of samples, so to repeat this process 1,000,000 times and in a very, very short time, where classical computers will take a lot of time to actually produce the samples here. Okay, so...
And these gray boxes are like single qubit gates.
Yes, so it's a qubit after one gates. So actually there are 2 parameters, which is paramount here in terms of complexity. One is that the number of qubits, and the other one is that it's the number of the circles. You can see that how many times it repeats the
cycle, the M on the bottom there.
Yes, exactly.
Right.
So 1, 2, 3 until M. So how many circles of operations that you have before one measurement to produce one sample? You might have a question. So if they are not able to produce the ideal bit stream, how do they know? How do they verify that their bit stream produced by the quantum device is correct? So actually, you're doing a method called cross-entropy benchmaking, and with that, you only need a fraction. You only need to calculate a fraction instead of all the correct probability distributions that you require to verify. So, but still, the verification would take a lot of time. For example, that you can see that on the right picture, that the list the complexity with the number of circles M. So you can see the 12 circles requires 2 hours for the classical computer to produce, and until at the 20 circles that it takes 10,000 years. But for this process, quantum processor, it takes only 200 seconds to do that. But this result has been quite controversial, and there's many challengers who challenge specifically it's the classical simulation method used in this case to get the 10,000 year. For example, the latest challenger is from this group that they claim that they could achieve 2 million bit streams in 5 days with only a 60 GPU computational cluster and with even higher fidelity. So we don't know whether this is still an ongoing battle between the fastest classical simulation and the quantum device.
So they're saying that it's not truly an example of quantum supremacy because they didn't choose the best classical method.
Yes, yes, because you have to compete with the fastest one. Right. So if you have a new challenger that can come with an even faster one, then your supremacy would be then be false. Yeah.
So it's like claiming supremacy of hardware.
Yeah.
But it obviously also depends on the complexity of the algorithm.
Right.
Exactly.
So it's not only does not only depend on the hardware.
That's like the dolphin thing, right?
Yeah.
Yeah, but surely the Google has the best hardware, but not the best algorithm.
So the fidelity here, they say 0.7. And so what was the Google fidelity?
Well, we can look at that. So
0.1%.
So the fidelity,
okay.
yes, here is the y-axis is actually the fidelity. So you can see it's quite low for 20 circles. So
Okay, so but it still takes them 5 days, right? So
Yes.
okay, fine. The fidelity is higher,
yeah,
but so what does that mean? Like, if they reduce their fidelity, then maybe they could do it also in 200 seconds.
no,
Like,
I think they're just saying that you don't need 10,000 years to do 5 days.
Yeah, but I mean, but even if it was 5 days, isn't that still quantum supremacy?
Yeah,
Because
it's still
5 days is longer than 200
Yeah,
seconds.
in that sense, yes, it's still quantum supremacy, but well, not that secure, maybe.
Okay, so it needs to be like vastly longer, right?
Yes.
In order for it to be
I don't know,
quantum
but
supreme.
maybe you can.
So what is vastly longer? Like 100 times?
Well, I mean, 5 days is kind of within the range of classical computers.
Like it's classically solvable.
Yes,
You can
exactly,
conceivably
kind
run a
of.
classical
I see.
computer
Yes.
for
I
5
see, I
days.
see.
Yes, I think that's
Okay,
a probably
okay,
idea.
that's-
10,000 years, like
I see, I see. So it's sort of more like, it's impossible to solve
Exactly.
on a classical computer. Okay.
Yeah.
So you're, I guess, comparing it to like human lifetime. That's your
Well, yes, I think.
time range.
Yeah. But I mean, so what does this paper actually claim? That it's, that it's not quantum supreme or?
Well, I think they're more like they are proposing a better simulation method, and so they show their result that we did better than the classical simulation that Google did, but they didn't really go in outside of this.
I see. They didn't say Google is wrong.
No.
No, they don't want to.
Well, Google was wrong in that sense. Well, in terms of classical simulation, but
But I mean, this is always a cat and mouse game, as you say, right? So
Yeah.
I mean, that's the nature of quantum supremacy.
exactly, exactly.
That it's not like it's quantum supremacy forever. It's only,
Well,
only until somebody
Yes, but
comes up with.
what is following is actually kind of maybe we can claim it for much longer than this. But what about computer science say about that? So here that they have it is a very commonly known thesis in the computer theory. Now we have the extended church Turing thesis. It was saying that so all the computational problems. So because this thesis was proposed, the original version of this thesis was proposed much earlier than the modern computation took place. So it was saying that with the abstract idea of the Turing machine, they show that if any problem can be solved by realistic physical devices, can be efficiently solvable by probabilistic Turing machine. So if you have a problem which is somehow proved that it cannot be efficiently solvable by probabilistic Turing machine, and it will not be able to solve it by any realistic physical device, also including quantum device. So quantum device is kind of exception here that might be able to break and to challenge this thesis to show that, okay, I have a quantum device could, solve some of the computational problems which are not efficiently solvable by the probabilistic Turing machine.
So the quantum computer included in the probabilistic Turing machine?
Yes.
Oh, it is? Okay.
Yeah, it is.
Okay.
So that's kind of thing that people didn't expect, maybe. So there's a potential that this could be wrong. So the most common thing that people would know is P versus NP problem is one of the millennial problem. So the most common known is the P class. Well, it's called. So first, this problem is called a decision problem. The decision problem is that some problem that you can verify very quickly. So there's, for example, 3 addition or multiplication, and also solving puzzles. They can solved by a deterministic Turing machine in polynomial time. And they are very easy to solve and very easy to check. And this easy here is more in terms of polynomial time, solving. So, and this is the most basic class, the P. And so the one behind it is the MP that can be solved by non-deterministic Turing machine in polynomial time. The computational time will will scale exponentially with the input. So, but of course, I mean here that when I say that hard to solve and easy to check, means that the problems that end in NP but not NP, which in the more technically terms is the NP complete. So, for example, the Sudoku is this kind of problem. So, and people have long eager to say that whether P is equals to NP, but I think it's still very far to prove or disprove. So, and these two are more like decision problems. And so the answers are very easy to check. For example, Sudoku, it's hard to solve it, but once you get the answer, you can just check very quickly, right? But another problem is called the counting problem. Problem is that instead of are there any, but you want to see how many are there. So for example, the P sharp P is counting, for example, counting the number of accepting the passes of polynomial time non-deterministic Turing machine. Is like, for example, NP is like how many are there for NP problems, like solution. So it's harder to solve and hard to check. So and for example, the Boson sampling, which we're going to be, because I think the time limit, which we're going to be in the next video of this.
There's no time limit.
There's no time limit? Wow. Okay, there's a slight limit.
YouTube can go for, I think, days, right?
Well, the attention limit, you cannot.
That's right.
But so the permanent that is originated from the Boson sampling problem is in the sharp P problem. So it's a sharp P complete. So it's in the sharp P, but not NP or P. So it's a hard problem. So it cannot be solvable by the probabilistic Turing machine. But if we can find a quantum device that can efficiently solve by a quantum device, then this thesis would be challenged. So in this sense, the Boson sampling is at a more concrete ground in terms of quantum supremacy, because it's kind of based on the quantum computational complex theory. But the random circuits, there's no proof of it being in sharp P or. Well, I'm not sure about that. I don't think it's not really.
I mean, it's considered hard, but somehow the Boson sampling has been proven to be in this sharp P. But I
think the random circuit is not really, you can really characterize as an MP or sharp P problem, I think.
No?
For example, the algorithm itself is evolving, maybe shows that a better method is being proposed. So here that, for example, if you show that the Boson sampling, well, we'll talk more next time, but here that if you show Boson sampling can be efficiently solved, then, this hierarchy would collapse, all this, you can get a shortcut from this sharp P to an MP, but I think for random circuits, you don't have that. But maybe I'm wrong.
How's the proof usually down? Does it require a specific algorithm to solve the problem and then find the complexity of that algorithm, or you can prove it based on more?
I think it's more like you build a bridge. You can say, okay, this problem is equivalent to that problem, and that problem is proven to be an NP problem, and so this problem. Yeah. So if you manage to solve this problem, you can use this problem to solve that problem, which is the NP problem. I think it's so. But sometimes you will find a problem which is nowhere to connect it. So maybe random circuit is kind of like that. But I'm not sure.
I think it belongs to a certain subclasses, but the relation of that subclass to other computational classes has not been proven yet.
Just one more mention that So the problems can be solvable by the probabilistic Turing machine. Is called a class called BPP, and it's kind of similar to MP, but it's of course it's within the range of sharp P. So
Discussion time.
Are there other controversies other than the Google paper?
So the paper is more about the indistinguishability, about how it will affect the boson sampling problem. So I think I will explain more in the next video.
Oh, that's your paper, yeah.
Oh, which one?
Oh.
So you're not talking about it.
I was just asking you.
So can you just give us a tip of what? Give us an insight. We are not saying tell us everything.
Inside of
Sneak
what?
peek.
Of what?
A trailer.
Yeah.
Yeah, a movie trailer.
Teaser.
A teaser.
Yeah.
Okay, what is the Russian or rather the Chinese quantum supremacy claim all about?
Mostly because their experimental parameters are outside the range of the theoretical investigation that the people have done before. So there are a lot of parameters. For example, their efficiency of loss is very high, and they have very high screening parameters, and it's not really so people have investigated. So people have doubts whether this parameter would be a reason that their supremacy is not really could be challenged.
So quantum supremacy has been achieved
Which one? This one?
in any form?
Have been achieved?
Yeah.
Well,
Well, I think so. Yeah. Right.
well, I mean, so
It's real and it's
the
caused by man.
the problem is always you can never have the ideal case. For
Yeah.
example, of course, if the experiment is really follows the ideal case, have the very high, near one efficiency, near one indistinguishability. Of course, and the experiment will definitely achieve a quantum supremacy. But in experiment you can always be imperfect. You always have this thing and that thing you don't want, and you cannot get rid of it. So there could be leave a backdoor for algorithm to actually simulate efficiently. So
maybe there exists a classical algorithm that estimates.
sure.
Okay.
There is, it's very much possible.
Why can't you just do quantum supremacy with just some very complicated quantum system, and just say, why can't I just go, here's a quantum simulation, here's a very big molecule, and then I just made it in the lab, and then that's it.
That's very good question, and there are a lot of people are saying that because of the because it's already achieved in many cases for BEC or I don't know. But I think it's because from the terms of quantum supremacy that especially from the people who propose it, they will think that it's more like a specified task, more well formalized. You can also give it just one sentence problem, for example, then you can link to a concrete problem which is already proven in the complexity theory that to be hard. I think it's more in this kind of sense.
I see. So the physics problem is too physicsy, and it's not a real problem.
Yeah, well.
So it's not like they can't do it, they just don't want to because it's too physicsy.
Yeah. Well, but so in that sense, it's kind of, so that's why the boson sampling was attractive in that sense,
in
right?
the sense.
Because it could be linked to more of a computational problem.
Yes,
right?
very concrete.
Yeah. And then so the Google one, so the random quantum circuit is in a sort of a gray zone if you go by that definition.
I think that because this quantum random circuit is the most natural quantum device we could come up with, depending on the existing technology. Sometimes you use what you have to cook, so
It's a good quote. Yeah.
so they have that technology and they could do this, so they choose to do that.
So thank you for watching, and if you enjoyed the video, then please like and subscribe. So see you next time. What? We never clap. We never clap.
Clap outside.